Hey gang, and welcome back to another worksheet solutions walkthrough for the worksheet reactions with conjugated systems. Okay gang, so now that we are easing our way into jOeCHEM 2, we've talked about conjugated systems at this point, right? We've talked about a network of sp2 atoms all in a row, more than, 3 or more. We can see how electrons are delocalized, and that can affect not only the stability of a molecule, but how molecules behave in reactions that we've done and reactions that we will do in the future. So if you're here, you've tried the worksheet. Awesome. If you're looking for answers, you're in the right spot. Enough of me jabbering, let's go. Okay gang, so in attacking problem 1, I'm going to do the first 3 of the 5 reactions first, and then I'll do a pause, do a little cleanup, and we'll attack the last 2 in problem 1. Okay, so if we take a look, these first 5 problems are just supposed to be designed to show you that we can do reactions that we've done in the past, but now that we introduce topics like an allylic position where we can have a charge that's stabilized via resonance, and even more so than that, a conjugated system, how does that change some products that we can get? So if we take a look at problem 1, the first part of problem 1 up here, hopefully it's obviously multi-step, so we'll take it one step at a time. So hopefully what you're thinking is, we see butyl lithium, okay? Now, when you see butyl lithium, I hope you're thinking wicked strong base, right? Butyl lithium looking to rip off any proton. Now, if we take a look at 2-butene that we have here, we really have 2 options here. We have the sp2, sp2 carbon, that has a hydrogen. We can deprotonate that position to start, because the first thing we're gonna do is an acid-base reaction. But if you actually look at a pKa table, and the reason I chose this problem was to really go along with the theme of conjugation, allylic position, the most acidic proton you're going to have in this structure is the allylic position. The allylic hydrogens are just a smidge more acidic than sp2 hybridized, sp2, or you could call these vinyl hydrogens, or if you could just call them, alkenol hydrogens. But the very first thing we're going to do, butyl lithium, very, 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 very basic, right? Kind of looks like this. It's just going to be an acid-base reaction where you're just going to rip this proton off. We're going to put a lone pair on this carbon right here. So the very first thing after the first step, if I'm going to kind of draw a little bit right here, is we're going to make an allylic nucleophile, right? We're going to put a negative charge on this position right here, and that is favorable because we know this is resonance stabilized. Whoops. So I can absolutely do something like this. We know it's resonance stabilized. Amazing, right? That's what we're going to do in the first step right here. This is the nucleophile we're going to carry forward. So if we look at 2, okay, now we see why step 1 made sense. We have an aldehyde, right? I did abbreviate CHO on the worksheet, just giving you a different look. You know what I mean? So what we'll do in that next step, I'll redraw my aldehyde like this. Benzaldehyde to be exact. This is going to attack right here. Electrons kick up. Just, good old nucleophilic attack. So what we have here, and I'll even draw it more like this. Right after the attack, we do have an O-, and then off of this dotted carbon, right, we're bonding to this, what was the allylic carbon. So there's my dot carbon. That's the first carbon right here. So you can see how that would go. And then this third step is just a protonation cleanup step, so we don't have an O- floating around at the end. So I'm not going to show that. I'm just going to show the protonated version like that. And also, if you're wondering if we had to worry about drawing resonance here or whatnot with, after the deprotonation, right, we're going to want to leave this negative charge on the most sterically available carbon, the primary carbon. That's where the attack can happen. Also, if we're going to think alkene stability, the alkene is most substituted in this position versus this right here. So if you're wondering, oh Joe, how do we not know, can we tell if this thing is going to flip resonance-wise and then we'll do the attack? No, it's just going to stay this way because of the alkene stability, and sterically this will work out better for the nucleophile in attacking. So in problem 1, it was just an acid-base reaction followed by an attack on a carbonyl carbon and a protonation step to get it to go. But I included it just for the acid-base reaction right off the bat, just because acid-base, I always forgot about it. I don't want you to forget about it. Okay, so in problem number 2, and I'm gonna erase this right here just to make some room. In problem 2, we're bringing back some other alkene chemistry, right? So this is tail end of OChem 1. So what we're going to do is we're going to halogenate the double bond, but it's going to be one of those scenarios where we get the reaction going with our halogen, but we have water as a solvent and it's going to participate. So just as a little primer, what we'll do right here, double bond, doesn't matter which one because we're symmetrical. We'll grab one of the chlorines, we'll boot this chlorine over there. So the very first thing we're going to generate, I'll draw it up top here, looks like this. Didn't touch this double bond at all. And remember, this is when you make that cyclic chloronium ion, right? So we're going to look something like this. But remember, we can draw resonance here, and we're not going to look like this cyclic chloronium ion. We can definitely give electrons like this, or the other way to chlorine. And I hope what you're going to see is I drew that specific resonance move on purpose because you will form an allylic carbocation, right? I'm not going to put the carbocation on this carbon right there. I'm not going to give chlorine these electrons. I'm absolutely going to give chlorine the electrons right here in resonance, and this is going to be the resonance hybrid that contributes most to the overall structure because of the fact that it is now resonance stabilized because it is an allylic carbocation, okay? So really, this first move, I didn't even have to show you the cyclic chloronium ion, and in fact, I'm going to actually walk that back. I'm going to show the chlorine adding, and I'm going to show it added here because we know allylic position, the carbocation is going to be best there. Now at this point, right, now that we've got chlorine starting the reaction, we have a carbocation. Now this is where our solvent, there's so much more of it than the Cl2, right, especially the Cl- that we just produced, it will attack. However, right, it's going to attack this structure as it looks like, as it presently is, but we'll also have the ability to attack it in this form as well. So we get two products here. That's the result of this problem. And I'm going to draw them in blue. So we'll have the chlorine here in both scenarios, but here we'll have OH because water is going to be doing the attacking, right? Water is going to be the one coming in and attacking. So we'll have this here. This is from this product right there. And then from over here, right, plus, we will have this as well. Chlorine up top, right there. So we'll get two different products, but one will be this. This is, if you will, we do the attack without the resonance, without rearranging. This is our product after we rearrange. And I'm not saying what the percentages and splits are. I'm not telling you that. I'm just saying we will get a product mixture with these two products. One, if we do this reaction because of the conjugation and the resonance stabilization of that allylic carbocation. Okay, gang. Now, last but not least, we have a little bit another situation, right, where you definitely can see we have HBr. We're going to be protonating double bonds that we have present down here, and we're going to have some resonance to draw. So what I want to do is we have two situations. I can protonate this double bond, where I will put a carbocation right here because of the allylic position, and on, conversely, because of this double bond, I can protonate this double bond and put a carbocation right here because it is allylic to that double bond. So let me draw those two initial carbocations. I'm going to draw them right here. There's one. That would be if I protonated this double bond right here, because I surely won't put the carbocation over here. And we'll also have, I'm going to erase this up here a little bit. We will have this carbocation as well. Okay? So what we have to honor is we can have Br minus attack this carbocation right off the bat. So what I'm going to do is I'm going to draw that product. And remember, we're all about just the regiochemistry here, not the stereochemistry. But I hope you can also see with this structure right here, I can absolutely draw resonance like that. And then I've generated this carbocation. So just from this structure alone, I have two products. Let me erase that. I'll put a plus sign right here. Oh, hold on, gang. Sorry, I'm running out of room. Definitely needed a little bit more space to do this problem. But I think you can see we get these two products from this initial carbocation formed. Two products because we can draw resonance. Same deal up top. I think you can see I can absolutely move this over there. Let me see if I can squeeze this in. Now I have the plus charge over here. So I can have two products formed from these two intermediates. So to draw them, what I'll do is I'll kind of section this off. So I have this product as well as this product right here. So in problem 1, gang, we had the first problem, kind of the relevant thing was the acid-base reaction, right? Ripping off the proton in the allylic position, making a good nucleophile, attacking an aldehyde, protonating it up. Here, we did the halogenation of a double bond. We saw that we just had to generate the first part, the part where the carbocation was formed, draw the resonance. So then we took our two intermediates, finished the reactions by attacking with water. And then down here, we had even more work to do, right? We had 4 different products, right? There we go. 4 different products. So we generated the 2 initial carbocations. We drew the resonance for each. Then we attacked with Br- to finish them out. Let me just make sure I didn't screw that up in doing that. Okay, we look good. Okay, so gang, that does it for the first 3. Let's finish out problem 1 with the last 2. Okay, gang, 2 more problems to finish out problem 1. So if we take a look up here, right? 2 more, but nothing we can't handle. So if we take a look at this first one. So again, more alkene chemistry coming back at you. So we do see we have a conjugated system right here, but, symmetrical. And first step, we, blast it back to alkene chemistry. We're going to make an epoxide. Because if we treat a double bond with MCPBA, we get that 3-atom system. We get that lovely epoxide. It doesn't matter which one you pick. So after step 1, I'll just kind of do this down here. You could imagine we have something like this. And again, no stereochemistry, just regiochemistry here. We're just trying to get the array of products correct when we have conjugated systems and how that impacts our, changes our reactions. So in step 2, so we have an epoxide. Now maybe you're seeing why, what's going on. Very similarly to that Cl2H2O problem, the reaction in problem 1, we're going to be doing another thing here where we're going to have a positive charge. So in step 2, right, we know attacking epoxides can vary whether you're in an acidic environment or a basic environment. Here with 2, you can see we're going to have acidic conditions. The reason why that is going to then cause some interesting things to happen is because we know that there's resonance right at the beginning when we protonate that oxygen, which happens in acidic environments when you have an epoxide. So at this point, right, we can draw resonance. I could show this bond swinging up over here, but more importantly, and I think what you're probably sitting at your computer saying, Joe, I know what's happening, we can definitely draw resonance with that bond going up like that, which means we have a positive charge in, you guessed it, the allylic position. So really this blue structure is what we're working with. I drew the purple just to show you how we got there, right? So let me erase this. So at this point in time, right, we have our ethanol is going to be our nucleophile. We can definitely attack at this position, but what I think you will all agree with is we can draw this resonance up like this, like we can with conjugated systems. That charge is delocalized. So you can see instead of the charge being next door to our hydroxide in a 1-2 relationship, now we kind of have a 1-4 relationship going on. So if you were given this on a test without any type of temperature conditions, you'd have 2 products, right? We would have, because it's at this point that, let me put it this way, the ethanol comes in, the oxygen, the nucleophilic atom comes to attack, right? So we have 2 different types of attack right there. So in the first product above, right, you can see, I'm going to erase to make some space. We're going to have the ethanol right here, OET, right? I skipped the part where oxygen attacks. You still have the hydrogen attached. You have a plus charge, and then there's the cleanup step. So we have this, and then you can see that from what's drawn right below, double bond still down here, you have the OET in that 1-2 fashion. Let me clean that up a little bit. OET, there we go. So it's these two products you get, and it comes from the fact that, here I'll even put step 2, when you have that protonated oxygen in the epoxide, right, really we know that exists like this with the allylic charge right there. You can draw resonance, and that gives you the array of products that we would see. Okay, to finish out problem 1, we got this down here. Wanted to throw a little radical action at you, because the radicals always fall under the radar. So, we even had a video on this on jOeCHEM about, you know, you can't just do the lovely free radical chain reaction with alkenes, because you'll end up halogenating the bond across it, right, doing that anti-addition versus doing the free radical halogenation that we've come to know and love. But no fear, because NBS can do it for us. So we know that this will create a radical intermediate right here. We will create through the mechanism, and I would highly encourage, if you're wondering what that mechanism looks like, to go to that video on jOeCHEM. We will have this radical right here. We will definitely generate, you know, after step 1, I'm going to use some space. So we'll have this, and I'm going to use the space up here to show that after step 1, we will certainly have this right here. But I also want to show that we have this intermediate right here. This intermediate can rearrange. And weirdly enough, I'm going to conveniently draw this over here. We will draw a single-headed arrow going like this. I'll take one of these electrons and I'll move that over here. And then this last electron goes right there. So the other radical that we create looks like this. Drawing it a little big because I know it's in the corner a little bit. Double bond here, radical there, okay? So we're also going to generate, well, I'll do plus. So we're carrying forward 2 things, if you will. Right, oh, that's where the bromine will go. Bromine will go right there. Okay, so after step 1, we have these 2 alkenyl bromides, okay? Or allylic bromides, whatever you want to call them. So, second step. Now we're going to be doing elimination, right? Potassium T-butoxide, and flashback to elimination. This is our big bulky base, right? So if we have to make a decision, we're going to make a Hofmann elimination. We're going to look for, you know, the lesser substituted double bond to create, because T-butoxide is so big and sterically hindered, it's not going to try, it won't be able to get the hydrogen that might be a little sterically hindered that will give us the most substituted double bond. It'll go for the easiest hydrogen to grab, which will result in the lesser substituted double bond. So if we take a look up here, right, I think you can see we do have the option of eliminating this way, because we have a lovely hydrogen right there, and that would be a really substituted double bond. That would be tetrasubstituted, tertiary, tertiary. But knowing this is T-butoxide, we're definitely going to instead go for this double bond right here. This will be a tertiary, secondary double bond. So one product you will see is this right here, and you can see that we also get a conjugated system out of it, which is amazing, right? sp2, sp2, you know, sp2, 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 sp2. Cool. That's how we got this. This was T-butoxide. Now, what will we see down here? Do we have any elimination choices to make like we did in the first respect? Not really, no. We only have one option, and it's this option right here, right? There's a hydrogen here. You know, we're not going to eliminate over here. We're just going to do the acid-base reaction right there. So the other product we form looks like this. And again, you see we get that lovely conjugation as well. So you get this product, you get this product. So gang, problem 1, all these various reactions was just to throw a couple scenarios at you and show you how conjugation can affect the array of products you get, right? There's really nothing different about anything we've done so far. You know these reactions. You just have to pause, look for where the resonance is, and draw it, and then you get the array of products. Whereas opposed, you know, Chem 1, we just had 1 product, maybe 2. Anyways, gang, that was problem 1. Let's move on to 2, which I promise is a lot shorter. Okay, gang, rolling on into problem 2. We are tasked with we are given two different reactions, reaction A, reaction B. And all they are both SN2 reactions. You can see that we have an alkyl chloride, we have sodium cyanide, Cn minus will attack from the backside, replace the chlorine, and that's exactly what happens down here. However, I think you can spot the difference, right? One is an allylic halide and the other is not. So, part A is which of these reactions is faster. And even going along with this theme, if you have no idea what the answer is, I think you can make a good guess that it's going to be reaction A. Reaction A is going to be the faster, more favorable reaction. Now, the harder part, why? And it comes down to the transition state. So, quick reminder that in SN2, if we were just going to zoom in on either of these carbons, forget allylic position aside, what happens in the transition state is this bond is forming from Cn minus, is a lone pair from Cn minus. This bond is breaking from chlorine, and what we kind of have is a temporary position where this carbon doesn't have 4 bonds exactly, and it's sp2 hybridized in a way. So when you have this type of, and I didn't fill in the fact that there are 2 hydrogens right here, and then this bond to carbon, so they fit in around here as well. Those are the true bonds, and these half bonds are in there while this carbon is in this intermediate state. This transition state is stabilized by the additional p orbitals from the sp2 carbons that it is adjacent to. So being allylic, being in the transition state has a payoff. You mimic and you gain the benefit of a conjugated system for a brief second. The transition state is stabilized in this scenario, whereas none of that exists when you are fully saturated. Saturated meaning no double bond, right? Saturated meaning all carbon-hydrogen bonds are there, versus up here we have a carbon-carbon bond that replaces a CH bond, a CH bond. So, because of that reason alone, you would expect A to be faster because the transition state is more stable, which means the energy to get to the transition state is less, which rolls us into part C, is to show this on an energy diagram. So what I'll do is this is for A, this is for B. So, by exactly what I just said. So we pretty much start out in the same place, roughly end at the same place, right? Let me make sure these are to scale, right, roughly. But what's going to be different, and what will illustrate the difference in reaction speed, is the transition state for A is lower than that of B, because the transition state, the energy to get there is less than, so I'll put delta EA A for reaction A, and then this is delta EA activation energy B, I'll do lowercase letters. You can see that I on purpose made sure that A was, the delta EAA was smaller than delta EAB, right? Because of the fact that the transition state is more stable, because of the allylic position and the conjugate, effective conjugation, the stabilization of the p orbitals. It takes less energy to go from this state to still an unstable state, but one that's not nearly as high energy as the one we see in B. So again, that does it for problem 2. Let's finish this out with problem 3. Last but not least, problem 3, and we are getting to thermodynamic and kinetic control. So if we take a look at this lovely reaction right here, you can see there are no products given to us, and that's because we're going to use our big brains to predict them. So that's what A is, predict the products for this reaction. So hopefully what you can see is we have an alcohol. We know they're amphoteric. We know they can be both a source of H+, or they can gobble up H+, right? They can be an acid or a base. So we're in the presence of strong acid, this alcohol, right? Electronegative oxygen in there, going to grab H+. So the very first step, if I'm going to kind of draw down this way, is HBr will protonate the oxygen in the alcohol. So down here, I will have OH2+, right? We protonated our what was an alcohol up to OH2+, which will be a great leaving group in water. Because we're in a polar protic environment, you better believe SN1 is going to happen, meaning solvolysis will be facilitated that, water will leave. And what that does is, you guessed it, created a carbocation, but not just any regular tertiary carbocation. That is allylic. So at this point in time, if we're just predicting the product, right? I'm going to draw some resonance. I'm going to show this double bond swinging over, and I will draw the result of this resonance with the double bond over there. Carbocation moved to the primary carbon, still allylic, right? Now at this point in time, we can show bromine attacking in both positions, right? If you just ignore the resonance arrows, I'll attack there. I'll attack there. And up top, I'll draw the product so you can see we both have this bromide right there, this alkyl bromide, as well as, and give myself a ton of room, as per usual, this bromide right there. So these are our two products. Now we have to answer some of the harder questions. Which product is the product that you would get under thermodynamic control? Which one would you get under kinetic control? So remember, it comes down to alkene stability, and if you have the time to rearrange based on your, the heat content of your surroundings. So if we take a look up here, hopefully you can identify that this is the more stable double bond. This double bond right here, you can see 1, 2, 3. This is tri-substituted. This double bond over here is just mono-substituted. So because this is more stable, right? This is our the product we would get under thermodynamic control, and this one, the one that does not rearrange, the one that just forms faster, is what we get under kinetic control, okay? So that takes care of both A and B. Now C suggests some temperature conditions, right? So you have to remember what conditions results in which product. Remember, with kinetic, we don't need any, the product is just trying to form as fast as possible. That's when you're at lower temperature. So if I'm gonna go along with the textbook that I usually reference, I would say, you can choose 0 degrees Celsius. It's just gonna be something that is colder, right? Now with thermodynamic, you want more heat. You want to be able to have lots of excess energy around you that will facilitate and allow the molecule to rearrange, go through, the resonance move. And I know it happens very fast, right? But on paper for us, it's the resonance move, get that more stable double bond. So we could say this is something like 20 degrees Celsius or whatever temperature change or temperature range I meant to say your teacher uses in your class. Please go with that. The point being, thermodynamic control happens with higher temperature. This happens lower temperature relative to that. Okay, gang, I hope if you were looking for answers, you got the ones you were seeking. If you're watching this video, that means you've financially supported jOeCHEM, and I just wanted to say thanks. You're the best for watching, and you're the best for supporting the website. I'm so happy you're using jOeCHEM as your tool to conquer carbon now, and I hope you're using it to the very end of your organic career. But if anything, I hope to see you all in the next video.